Numerical aperture, abbreviated NA, is a single number that tells us how much light a fiber can collect from the outside world and still stay trapped inside by total internal reflection. Imagine the fiber core as a narrow tunnel and the surrounding cladding as a higher wall. Light that enters the tunnel at a shallow enough angle bounces off the walls and keeps traveling forward. Light that comes in too steeply will spill out. ANA quantifies that steepness limit. Mathematically, Na equals n0 times sin theta max, where n0 is the refractive index of the medium, outside the fiber, normally air, n0 approximately 1. And theta max is the largest external angle measured from the fiber axis that still results in guiding. A larger Na means the fiber can accept light from a wider cone, which is why multimode fibers high Na are easier to couple with LEDs, while single-mode fibers have a very small Na and need precise alignment. Explanation for a step index fiber: the core has a uniform refractive index N1, and the cladding a lower uniform index N2. Light traveling inside the core strikes the core cladding boundary at some internal angle phi. Guiding occurs only when phi exceeds the critical angle phi sub c for total internal reflection, which is given by sin phi sub c equals N2 divided by N1. The geometry of the ray can be expressed in terms of the external launch angle theta, measured in the surrounding medium, usually air. Using simple trigonometry on the ray diagram, we find sin theta equals N1 times sin phi. And at the limiting case phi equals phi sub c, sin theta max equals N1 times sin phi sub c equals N1 times N2 divided by N1 equals square root of N1 squared minus N2 squared. Because the external medium is air N0 approximately 1, the definition Na equals N0 times sin theta max simplifies to Na equals square root of N1 squared minus N2 squared. This result shows that Na depends only on the difference between the squares of the core and cladding indices, not on the absolute values themselves. The acceptance angle theta max is the largest angle with respect to the fiber axis, at which light can enter the fiber from the outside and still be guided. Since Na equals N0 times sin theta max, and for most practical cases N0 is approximately 1 air, the relationship becomes very simple. Theta max equals inverse sine of Na. Think of the fiber end as the mouth of a funnel. The Na tells you how wide the opening of the funnel is in angular terms. If Na equals 0.2, the funnel accepts light within a cone of half-angle inverse sine of 0.2 is approximately 11.5 degrees, meaning any light coming in at a steeper angle will miss the funnel and be lost. This simple formula is used in every fiber optic connector specification to guarantee that the launch optics, laser, LED, or lens, produce a beam that fits inside the allowed cone. Suppose a step index fiber has core index N1 equals 1.48, cladding index N2 equals 1.46, and operates at wavelength lambda equals 850 nanometers. First, compute the numerical aperture. Numerical aperture equals square root of N1 squared minus N2 squared, equals square root of 1.48 squared minus 1.46 squared, equals square root of 2.1904 minus 2.1316, equals square root of 0.0588, approximately 0.242. Because the surrounding medium is air, N0 approximately 1, the acceptance angle is theta max equals arcsine of numerical aperture, equals arcsine of 0.242, approximately 14.0 degrees. Interpretation: light emerging from an LED that forms a cone of half angle less than or equal to 14 degrees can be coupled into this fiber without significant loss. If the LED's beam is wider, a lens must be used to reduce the cone to fit inside the 14-degree limit. A quick sanity check. A typical multimode fiber with N1 approximately 1.49 and N2 approximately 1.45 gives numerical aperture approximately 0.29 and theta max approximately 17 degrees, which matches common commercial data sheets. In a step index fiber, the index jumps abruptly from N sub 1 in the core to N sub 2 in the cladding. The Na derived above, square root of N sub 1 squared minus N sub 2 squared, assumes this sharp step. In a graded index GRIN fiber, the index changes gradually, usually following a parabolic profile. N of r equals n sub 1 times open bracket 1 minus 2 delta times open bracket r over a close bracket squared close bracket for 0 less than or equal to r less than or equal to a, where delta equals n sub 1 minus n sub 2 divided by n sub 1, and a is the core radius. Because the light experiences a continuously changing index, the effective Na is still given by the same outer core to cladding difference. That is Na approximately equal to square root of 2 n sub 1 squared delta, approximately equal to square root of n sub 1 squared minus n sub 2 squared. The key difference is that graded index fibers reduce modal dispersion. Rays taking different paths arrive at the end at nearly the same time, which is why GRIN fibers are used for high-speed multimode links. Practically, the acceptance angle theta max equals arcsine of Na does not change dramatically between step and graded index fibers of the same n sub 1, n sub 2, and core size. What changes is the internal ray path, not the external cone that can be launched. Therefore, when designing a system, you can use the same Na formula for both types, but you must consider the index profile when predicting bandwidth and dispersion. Explanation: the V number or normalized frequency combines the fiber's geometry, wavelength, and Na into a single dimensionless parameter. V equals 2 pi a Na divided by lambda, where A is the core radius and lambda is the operating wavelength in the same units. V tells us how many guided modes the fiber can support. If V is less than 2.405, the fiber supports only the fundamental mode and behaves as a single mode fiber. For larger V, the approximate number of guided modes M for a step index multimode fiber is M is approximately V squared divided by 2. Example, a fiber with A equals 25 micrometers, Na equals 0.22, and lambda equals 1/300 nanometers gives V equals 2 pi times 25 times 10 to the minus 6 times 0.22 divided by 1.30 times 10 to the minus 6, approximately 6.7. Since V is greater than 2.405, the fiber is multimode, and the estimated mode count is M approximately 6.7 squared divided by 2 approximately 22 modes. This quick V number check is routinely used by engineers to decide whether a fiber will act as single or multimode for a given wavelength. Note that V scales inversely with lambda, so a fiber that is single mode at 1,550 nanometers may become multimode at 800 nanometers unless the core size or Na is changed. Total internal reflection TIR is the cornerstone of light guidance in fibers. It occurs when light travels from a higher index medium, core N1, to a lower index medium, cladding N2, at an internal incidence angle phi that exceeds the critical angle phi sub c, defined by sin phi sub c equals N2 divided by N1. If phi greater than phi sub c, the ray is reflected back into the core with virtually no loss. In the ray diagram of a fiber, the internal angle phi is related to the external launch angle theta by Snell's law. N0 times sine theta equals N1 times sine phi. Combining these two equations, and using the definition of Na yields the familiar Na equals square root of N1 squared minus N2 squared. Thus the critical angle is the physical reason why Na is limited. It is the smallest internal angle that still guarantees TIR, and it translates to the largest external launch angle, the acceptance angle, that the fiber can accept. Practically, when a fiber is bent sharply, the effective incident angle on the outer side of the bend can drop below phi sub c, causing some light to leak out. This is why bend loss specifications are important for cable installers. Question 1. A step index fiber has n sub 1 equals 1.50, n sub 2 equals 1.46. Find Na and the maximum acceptance angle in air. Compute Na equals square root of 1.50 squared minus 1.46 squared equals square root of 2.25 minus 2.1316 equals square root of 0.1184, approximately 0.344. Theta max equals arcsine of 0.344, approximately 20.1 degrees. Question 2. For the same fiber, the core radius is 4 micrometers and lambda equals 1,310 nanometers. Determine the V number and state whether the fiber is single mode. V equals 2 pi times 4 times 10 to the minus 6 times 0.344 divided by 1.31 times 10 to the minus 6, approximately 6.6. Since V is greater than 2.405, the fiber is multimode. Question 3. Explain why a graded index fiber with the same n sub 1 and n sub 2 can have the same Na but lower modal dispersion. Na depends only on the index difference at the outer boundary, so it is unchanged. Inside a graded index fiber, the index gradually decreases, causing higher order rays to travel faster in the lower index outer region, compensating for their longer geometric path. This reduces the spread in arrival times modal dispersion. Question 4. A fiber is immersed in oil of index n sub 0 equals 1.48 instead of air. Its Na as defined in air is 0.22. What is the new acceptance angle? Use Na equals n sub 0 times sine theta max. So sine theta max equals Na divided by n sub 0 equals 0.22 divided by 1.48, approximately 0.149. Theta max equals arcsine of 0.149, approximately 8.6 degrees.